Morning all, good afternoon all, good evening all in different parts of the world. My name is Farid Mistry, and on behalf of my colleagues, Janet Allen, Seish Kumri, Roger Xiao, Jelena Milisavljevic-Syed, Jitesh Panchal, and Dirk Schaefer, I welcome you to the 5th JMD webinar titled Design Engineering in the Age of Industry 4.0. The emerging paradigm of Industry 4.0 poses new systems design problems at the interface, note the word interface, of smart manufacturing, robust and flexible automation, distributed and reconfigurable production systems, industrial information of the Internet of Things, and supply chains. In the context of Industry 4.0, we wish to define design engineering. And design engineering in the age of Industry 4.0 necessitates a new model that encompasses the sustainability of product and service, user experience, and human satisfaction across a smart and connected value chain, as well as distributed and networked aspects of the product realization process. So no longer are we looking at design of a product or a service, but we're looking at design engineering in the age of Industry 4.0 as one that integrates, deals with all these issues that we put together. In this special issue, authors of 14 papers address recent advances in design engineering and have identified future research directions. In this volume, there are 950 papers that have been cited. And so it's a great repository for PhD students, for faculty, for researchers who wish to go and say, aha, what's the state of art in terms of design engineering 4.0? So on behalf of the co-editors got together and said, what is our goal? Why do we wish to put in this proposal to have a special issue? Our goal was to provide a basis for researchers to promote design engineering in the age of Industry 4.0. Industry 4.0 is a paradigm shift. And what we are looking for here is what is the paradigm shift in design engineering? In addition to the JMD criteria for evaluation, we added 2 further selection criteria. We received 33 papers, and we looked at the papers, included those papers that focused on promoting design engineering in the context of 4.0. And based on what was presented in the text, the authors identified future avenues of research. So these were 2 additional criteria that we put in to down select from 33 to 14. The outcome is that there is a lead paper, and that lead paper is titled Design Engineering in the Age of Industry 4.0. It contains 267 citations and references. These have been critically evaluated, so this is a great repository of information. Design Principles and Technologies for Industry 4.0, there are 4 papers, and the total number of references in these 4 papers is 294. Smart Manufacturing Technologies, there are 5 papers, and there are 230 references in these 5 papers. And Machine Learning and Data-Driven Technologies for Industry 4.0, there are 4 papers and 178 citations. So today, the 4 papers that we're going to be, we are focused on are Design Engineering in the Age of Industry 4.0, and the presenter for that, the recorder for that is Jitesh Panchal. Designing a shape performance integrated digital twin based on multiple models and dynamic data, a boom crane example, and Xueguan has recorded the video for that. Leveraging task modularity and reinforcement learning for adaptable Industry 4.0. Babak Heydari has recorded this. And knowledge-based design guidance system for cloud-based decision support in the design of complex systems. The lead author is Wang. Jelena has recorded it. So in the 14 papers, there are 56 authors, and they have identified over 950 papers and several research areas worthy of investigation. How have we organized this webinar? After I'm done in a few minutes, Jenna Sayer will play 4 recordings, one after the other, Questions will follow the playing of the four recordings. And at the end of the recording, Seish Kumari will be spotlighted, and he will take care of the dialogue, which will be between 30 to 45 minutes. It's live. And then Seish Kumari will hand over to Janet K. Allen. Janet will make a closing remark for 1 minute, and she will hand over to Faiz Ahmed with the invitation, who will invite all of us to join in an app called Gather Town. Our intention is to maximize the number of questions. So I request the audience to put things in the chat, the questions in the chat, direct them to a particular paper. And the authors have all been instructed to answer quickly and shortly, quickly and very shortly. And our intention is to cover as many questions as possible. And if there are some questions that have not been answered, we plan to turn out a document at the end of the webinar that we will circulate to all. So with that, over to you, Jenna Sayer. Please start the recordings.
This is an overview of the paper titled Design Engineering in the Age of Industry 4.0, which is published in the ASME Journal of Mechanical Design in the special issue with the same title as this paper. The paper is co-authored by Roger Jiao, Seish Komuri, Jitesh Panchal, Jelena Milisavljevic-Syed, Janet K. Allen, Farooq Mistry, and Dirk Schaefer. This is partly a review paper and partly a perspective paper. In this paper, we review the evolution of engineering design in response to advances in technologies that form the backbone of the emerging paradigm referred to as Industry 4.0. We also provide a perspective on the research challenges and opportunities for the engineering design community. Industry 4.0 refers to the fourth industrial revolution with the vision of smart factories and interconnected supply chains enabled by technologies such as Internet of Things, automation, robotics, cloud, big data, and additive manufacturing, autonomous vehicles, and delivery robots. It closely integrates recent developments in the cyberspace, such as the digital twin, digital thread, and cloud computing, the development in the distributed network control of physical equipment, and how humans interact with technology. Such a smart manufacturing ecosystem can be viewed as a human cyber-physical system. The key principles driving the industrial transformation include connectivity and interoperability among physical and virtual resources, and virtualization of physical equipment, big data captured by ubiquitous sensors, and information transparency and accessibility across the networks, decentralization of decision-making, modularity, and interactivity of the systems. And then finally, service-oriented business models that are enabled by such a distributed system and the broader availability of networked resources. To understand how the evolution of industry has impacted the evolution of engineering design, we go back to the first industrial revolution in 1770s, where industries attempted to leverage hydraulic and steam power to mechanizing operations carried out by humans. Design and manufacturing in that era mimicked the process adopted by human operators. About 100 years later, Industry 2.0 was enabled by electrification and development of production lines for mass production of goods. With the objective of maximizing production volume, minimizing cost, the focus of design was on standardization and part interchangeability to harvest economies of scale. Industry 3.0 was marked by digital revolution in the 1970s with increasing automation and the use of CNC machines. Designs were digitized and the data shared across processes to ensure high-quality products with tight tolerances. Design and manufacturing processes became tightly coupled, and CAD designs started being used as inputs to drive CNC machines. Industry 4.0 promises greater interconnectivity among different phases of the product realization process, all the way from customers to design to manufacturing processes to supply networks. Design engineers are now empowered to design products by utilizing directly the live product usage data. Customers can play an increasingly greater role in co-creating products. Industry 4.0 is empowering product developers to be more agile, responsive, cost-effective, and fast to market. Considering the human cyber-physical view of systems realization ecosystem, we propose a conceptual framework for Design Engineering 4.0 with design at the center that considers emerging roles of humans in the product realization process, whether as customers or as designers, the emerging service oriented business models, the developments in cybernetics, machine learning, and AI, and the physical system consisting of infrastructure, machines, materials, and transportation. We use this framework to identify strategic areas, research challenges, and opportunities in this paper. Specifically, there are new opportunities for design considering user preferences and how users interact with products and among themselves on the internet. There are new opportunities for evaluating how businesses can monetize services. There are opportunities for customizing products and services to user requirements while producing products of zero lot size and mass production costs. And then finally, how to design systems that can collaborate and adapt to improve product quality, process reliability, systems agility, sustainability of the systems realization ecosystem. Designing and developing products in the era of Industry 4.0 is fundamentally different from principles in the context of traditional design. For a holistic approach to considering the challenges in product development concerning the integration of Industry 4.0, it is important to examine a dichotomy between the principles of Industry 4.0, shown in blue, and the human, artifact, and process dimensions of design. In this paper, we have mapped these principles to 9 strategic areas for design engineering 4.0. First, the principle of connectivity, virtualization, and interoperability maps to the design of smart and connected products, the process of end-to-end digital integration, and customization and personalization for humans. The principle of big data and information transparency maps to the strategic area of data-driven design. The principle of decentralization, modularity, and interactivity is related to the areas of digital twins and intelligent design automation, extended supply chains and agile collaboration networks, and open innovation, co-creation, and crowdsourcing. Finally, the principle of service orientation and network resources is related to the strategic areas of product servitization and anything as a service, and platformization for the shared economy. Within each of these 9 areas, we have identified specific research issues that the design community can contribute to. For example, in the first area of smart and connected products, some questions that can be addressed include: how can the design process of smart products be directly influenced and improved through near real-time analysis of vast amounts of user data, automatically collated from prototypes and released products being used in diverse ecosystems of other interconnected smart systems? To what extent will computers be able to autonomously shape design aspects of smart and interconnected products or conceive new innovative features based on user data analytics, autonomous or semi-autonomous data-driven design and innovation? How can customer privacy and the ethical usage of data from interconnected smart devices be designed into smart products and corresponding legal framework, including the GDPR and new policies governing the usage of smart and interconnected products across countries? Now, looking at the 6th strategic area, extended supply chains and agile collaboration networks, some of the questions could be: what are the design engineering 4.0 principles and methods to be applied to ensure fail-safe performance of the entire virtual value chain for product realization, which includes product design, production planning, and the supply chain? How can the rapidly changing demand forecasts be used to dynamically adapt the value chain? How can the effects of disruptions in any part of the supply chain be rapidly mitigated through rapid and holistic redesign of the product, the manufacturing process, and/or realignment of the supply chain? Some of the other questions include: how can data from real-time events be infused into design and manufacturing processes? For example, how could the design of product packaging be adjusted to represent the shape of the mascot of a football team that won a derby? How can crowdsourcing be effectively leveraged for both not-for-profit and industrial or commercial design processes? How can various models of crowdfunding be leveraged in the design of commercial products? How can vast amounts of customer feedback on online platforms be leveraged to advance customer co-creation? Finally, how can data-driven approaches such as social network analysis be used to analyze and improve the behavior and performance of design teams to identify designers or teams of designers whose activities are likely to lead to breakthrough innovations more often than that of others, or to identify team members that hinder the innovation process through the design solution fixation? Finally, in this paper, we have provided a perspective on the research opportunities for the engineering design community under four headings. First, the human perspective, which is designing for the human experience. Second, from the business perspective, which is design as a strategic engineering activity. The third is a systems perspective, which is design as a human cyber physical system. And then finally, the cybernetics perspective, which is design with smart sensing and AI technologies. Within each of these areas, we have identified specific sub areas and identified research questions that are relevant to the engineering design communities and particularly the authors of the Journal of Mechanical Design. And then we also have a section on educating the future engineers for this emerging paradigm of Industry 4.0. With that quick overview of this paper, we look forward to further discussion in this session. Thank you.
Hi everyone, thank you for joining this webinar. I'm Dr. Xueguan Song.
And the audio is okay this time?
From Dalian University of Technology. I'm the corresponding author of this work, and the first author is my PhD student. I'm so glad to be here today and introduce our work to you. At the very beginning, I would like to emphasize that the current digital twin idea comes from my past interdisciplinary research experience, as I do have many research interests since I was a graduate student, such as finite element analysis of structures, computational fluid dynamic analysis valves, and circuit-based design optimization. Recently, I'm also doing some big data mining work. And second, the first paper is just the starting point for us. During the past 2 years, we have published 7 papers in Chinese or in English. So today's presentation contains not only the first paper, but also our recent work. Now let's get started with digital twin. I guess many of you have heard this word for many times during the past few years because it's a very popular buzzword. In theory, digital twin is quite simple. It's defined as a virtual representation of a physical object or system. As my background is mechanical design, so I've always been thinking, what is a use for digital twin? How can it promote design engineering in the age of Industry 4.0? So I tried to classify these concepts into different levels. The biggest is the ecology level, the middle one is the production level, and the smallest one is the product level, in which a digital twin of a product or a component could be created. Obviously, they have different objectives and different challenges. When we talk about the digital twin for a product, no matter what shapes, I think the performance, especially the mechanical performance, has to be guaranteed. So for use for digital twin for the mechanical design, it's better to integrate both of the information together. So that's the aim of our work, to design a safe performance integrated digital twin. Nowadays, creating a safe twin is not difficult because we can use sensors to capture the information. On the contrary, mechanical performance cannot directly observed or easily obtained. They have to be calculated. So there are many challenges. For example, there is no loading, boundary condition, or initial conditions. As we know, the physical system is a dynamic process, and it will change the conditions constantly during the operation. So how can we provide accurate boundary condition for the digital twin model? The second, the calculation is computational expensive. From my viewpoint, the performance twin is more like a real-time numerical simulation. It also requires a large amount of grid or elements, which will cost much computational resources and time. How can we speed up the calculation to realize the real-time simulation? Third, how to guarantee the accuracy. There must be some errors or discrepancy between the physical and the digital twins. How can we verify and validate the model or results? That's very difficult. Okay, let me explain our method to address the first problem. Took this POOM query as an example. We use the variance sensors, including the inclination sensors, encoders, pose sensors, and load cell to measure the initial condition. As the structure is originally fixed at some position, so we can use a very simple static force balances equation to identify the loading G. When the crane is moving with the dynamic data, such as the velocity, the position of the loading, the length of the Y rope, we can obtain the dynamic force at each pulley. To address the second problem, we use a diverse model. In detail, we use the analytical model to predict the performance of the Y rope and the pulley. That's very fast. To predict the performance of the main structure, of course, we need the finite element model because it can output the strength and deformation information. But the biggest problem is this took dozens of minutes for just one case. So we have to rely on some faster approximation model, such as the surrogate model, reduced order model, or AI model. In this case, a Gaussian process model is used to replace the original finite element model. Third, we use a multi-fidelity surrogate model to calibrate the digital model. Look at this picture. On the left side, we can place some shrinkage on the main structure and define the measure data as a high fidelity data. And then we define the numerical model as a low fidelity model. And we can create a relationship function like the first one. It means each high fidelity data could be expressed by a low fidelity data well through some nonlinear transformation. As long as we can get the coefficient in the equation, then we can calibrate the digital twin model. Okay, based on that solution or method, we give out the framework of SPIDT. In the outer circle, there are sensor data, numerical model, expert knowledge. In the center, there will be a AI model. It plays the key role to integrate different model, different data into just one model. And based on that model, we can do some scheduling, controlling, big data mining, and visualization. Well, that's the brief introduction of the theory. Now let me show you some demos. This is the digital twin of the boom query. On the right side, we can see some shape information first, such as the velocity of the loading, the angle of the boom, and in particular, when it's working, we can see the performance information, such as the dynamic force, dynamic deformation. It's quite useful for the design engineering or redesign of the product. Okay, this is the second one. When we were creating the first one, we find the interesting thing that on the online prediction of the first one is almost near real time, but the offline training takes so long time. So in the second one, we use beam element to replace the 3D solid element, which saves much effort and time for us for generating the sampling and training the model. This is the third one, digital twin system of truss structure. We can apply the force here to the truss structure. And the red line is measured stress at some point. And the black line is the digital twin stress. We can see that they agree with each other very well for most of the points. Besides these demos, last year we were so lucky to get some financial support from large and famous company in China, Sanyi Zhonggong, and completed a real industry project with them. This is the digital twin of telescopic forklift. and this system and software has been deployed in that company. Okay, let's see the conclusion. The current work, the current digital twin, I like to divide it as in 3 stages. The first one is the physical run one step, and the digital twin calculate one step. The second is the prediction. Physical runs one step, and digital twin predict many steps. And the third one is digital twin predict many steps, and then go back to the physical to control one step. So from that viewpoint, the current work is in the first stage, only give a way to build a useful digital twin, and the intelligent control will be the ultimate aim of the digital twin. To achieve this final goal, we have many challenges to address. For example, how to utilize big data and combine it with physics models to create a digital twin, to promote design automation, and to realize intelligent design. Okay, that's the conclusion, but not completed. I would like to take this opportunity to introduce the software to you, DDoS, data-driven design optimization system. It's very similar to the commercial software asset or model center. The biggest difference is that this system is a web-based system or cloud-based system. So everybody can use it for totally free. And many people can work together at the same time and in one project. Well, that's my presentation. Thank you. Thank you so much.
Greetings, everyone. My name is Babak, Heydari, and I am a faculty at Northeastern University and the director of the Magics Lab. I present this work on behalf of my 2 co-authors, Professor Mohsen Muqaddam, who is the director of the Human Times Machine Lab, and Qiliang Chen, a PhD student in the Magic Lab. Let me first try to briefly put this work in the context of Industry 4.0. As we all know, flexible automation is one of the main pillars of Industry 4.0. However, integration of robots in most industries is currently limited to structured operations, and interactions with humans are often limited to fully predictable settings, which obviously doesn't give us needed flexibility. The focus of this paper is a framework that integrates the idea of modularity with recent advances in reinforcement learning to create more flexible and customized automation, especially for human-robot collaborations. This work also relates to several areas of design engineering 4.0. Here I'm going to borrow an insightful table from a paper on the same special issue, notably modularity, together with decentralization, is one of the key principles of digital transformation for Industry 4.0. Our work also acts as an enabler for a few of the other strategic areas of design engineering 4.0 as shown in the table. So how do we go from the notion of automation in Industry 3.0 to the flexible automation needed in Industry 4.0? Using AI, and in particular RL, seems to be a good candidate. However, most of the current reinforcement learning methods are highly specialized to a particular task, and learning any new task requires long period of training and can be very slow, which in practice makes our reinforcement learning not that flexible after all. And that motivates the main research question that guides this work. How can a cobot, a collaborative robot, use modularity in reinforcement learning to create flexible automation by autonomously adapting to complex and unstructured Industry 4.0 environments? So just a quick recap on reinforcement learning. Reinforcement learning is basically learning by doing, using a Markov decision process model of an uncertain environment where an agent learns optimal policies for taking actions by experimenting with the environment and receiving rewards. And since the dimensions of the problem are large, we use neural networks for function approximations, hence deep reinforcement learning. More specifically, our work builds on the framework that uses a particular class of policy gradient methods, DDPG, suited for cases where we have continuous action space. Deep reinforcement learning has been powerful for many applications, especially complex games, but for complex Industry 4.0 problems, they are very slow and need many observations to learn a new environment. So the question is how to add more efficient adaptability to the learning process. And this brings us to the good old modularity, which is commonly used in engineering system design and is also recognized as a fundamental complexity management technique in many natural systems, including protein structure and animal brains. In our past work, we have developed some theories for the emergence of modularity in complex environments. And in this paper, we extended the idea of product and network modularity to the area of tasks and algorithms. The longer-term vision here is to move to co-design of modular algorithms and modular environments. So there are generally two approaches for modularizing reinforcement learning. The first one is based on hierarchical learning, where different modules observe the action of the agents, and then they receive different rewards. And then they cast their votes for what action should be taken. The behavior coordinator then aggregate those votes and decide on the next action. The second approach, which is what we use, is more direct implementation of the idea of architectural modularity, where we first decompose a set of expected complex tasks into a group of subtasks, then pre-train a neural network module for each of those subtasks. And then the agent decides which one of those modules to use for a given environment to set the values of the network for learning a new complex task. Here's an overview of our proposed framework for modular DDPG. And of course, more details can be found on our paper. We assume there exists an underlying decomposition function and start by restructuring the function by mapping the expected set of environment into a group of fundamental and reusable modules. We create an evolvable depository of task modules, and for each new complex task, we first decompose it, then either transfer one of the existing modules from the depository, if possible, or learn that subtask from scratch and add that to our depository to be used later. We finally compose all these transfer modules and perform the final holistic learning, which importantly is supposed to be more efficient than doing that holistic learning starting from scratch. We implemented a simple version of this framework using 3 robotic environments in OpenAI Gym. We wanted to show the benefit of modular reinforcement learning for different notions of the modules. When we use the simple fundamental modules, as in the case of like a simple reach task module, as well as cases where we use sub-modules taken from more complex tasks. For example, transferring the reach module of the push task to pick and place task or vice versa. So we experimented with 2 scenarios, one for the pick and place and one for the push task. In each scenario, we compared the non-modular DDPG to the modular DDPG using fundamental tasks and to the modular DDPG using relevant modules from other tasks. We compared these cases using 2 metrics. First, we look at the success rate of each method as a function of the length of training. We see that in both scenarios, the success rate of modular transfer learning is significantly higher than the monolithic DDPG, especially when the number of learning iterations is limited, or when the task is more complex, such as the pick and place task. We also see that the relative benefit of using simple task modules or versus modules from more complex tasks depend on the nature of the task, which basically makes a case for having an evolving module depository. We also compared these different schemes by looking at the average time to completion and got similar results. So this part is not in the paper, but since it's relevant to this work, we wanted to briefly mention it. Since we published this paper, We acquired a Sawyer cobot and have been developing customized environments based on the assistive gym environment developed at Georgia Tech, and have been experimenting with reinforcement learning for human-robot coordination for a series of tasks. Here, as you can see, the Sawyer uses a customized digital model of the lab space to help to pick an object from a shelf and hand it over to a human. And this is an ongoing work, and we're now looking at building realistic models of human behavior and introducing the modular reinforcement learning to increase the flexibility of these tasks. So this work was just the first step toward adding more flexibility to automation for Industry 4.0 applications. To achieve higher level of flexibility, we need to still address several important challenges. First, our agent needs to be able to adaptively define and redefine the boundaries of the modules based on the expected profile of the environment, rather than using a fixed depository of basic modules. Understanding dynamic modularity and incorporating it into reinforcement learning is an important enabler to do this. Furthermore, to have an end-to-end digital model of complex tasks, we need to have realistic computational models of human behavior, especially when it comes to using reinforcement learning for cooperative interactions as opposed to zero-sum interactions. Finally, most existing reinforcement learning methods are developed for stationary environments, whereas many of the complex tasks that involve multiple humans or multiple AI agents are non-stationary. So we need to better learn how to build flexible automation in non-stationary environments. This brings us to the end of this short presentation. We look forward to continuing this discussion in the rest of the webinar.
Hi everyone. Greetings from the University of Liverpool. My name is Milisavljevic-Syed, and today I will present our paper. Further in panel discussion, Dr. Wang, Dr. Lin Guo, and myself will answer your questions. So let's start with Industry 4.0. I'm not going to discuss what that is, but based on our research, we believe that Industry 4.0 is happening in 4 overlapping cycles. It started from building blocks concerning defining a generic architecture models for cyber-physical systems and creating foundations for cloud manufacturing architectures. Later, we had more mature adoption of building blocks, and right now we're exploring new opportunities of value creation from digitization and data, such as new data-driven business models, integration of supply chain, and so on. Now, in the next 5 years, we believe that there will be transition from digital silos into holistic, decentralized end-to-end ecosystem, and perhaps new understanding and definitions of term enterprise as we know of today. But as you can see here, the core pillar of this digital transformation are cyber-physical systems. So cyber-physical systems are actually complex engineering systems that include co-engineer interacting networks of physical and computational components. And there are different types of cyber-physical systems. As information and communication technologies advanced further, cyber-physical systems evolved to cyber-physical production systems as intelligent and autonomous interaction of CPS objects, enabling adaptive, secure, and on-demand manufacturing services. With AI, knowledge-based design, decision-making, service-oriented design, all that enables servitization and product service systems as a unique combination of products and services. Now, through human-computer interaction and social computing, CPS further evolved to cyber-physical social systems as integration of humans, computers, and the physical environment. And latest in evolution, you can see cyber-physical product service systems enabled by product service systems and cyber-physical systems technologies, AI, knowledge-based design, decision-making, cloud services, and semantic web technologies, all that provide value chain added services for all stakeholders in digital manufacturing transformation. In design of complex engineering systems, there is a demand for decision support in managing complexity, uncertainty, and knowledge. And by investigating the decision support characteristics in different complex engineering systems, we identified 3 research gaps, as you can see here. First, that the functional vision of decision support of complex engineering system is not clearly defined or sufficiently discussed in the literature, especially for different types of complex engineering systems, as we saw previously. Most of the design methods focus on each type individually, neglecting dilemmas in decision process management, such as synthesis, different levels of decision activities. Second gap is that there are no methods for interacting the management of complexity, uncertainty, and knowledge. The third gap is that there is the need for design guidance to implement the cloud-based decision support and to develop system architectures. In order to fill the research gaps, we proposed the knowledge-based design guidance systems, in short, KBDGS. This is the architecture for cloud-based decision support in which designers can manage complexity, uncertainty, and knowledge in designing engineering systems. Complexity management include 4 parts: the management of system complexity, design complexity, process complexity, and organizational complexity. As you can see here, the CDK closed-loop guidance system is presented. Now, in terms of uncertainty, there are different sources of uncertainty that we identify and that can be managed. For example, uncertainties in problem modeling, the decision process, and robust design exploration. And very important, a significant amount of reusable knowledge needs to be captured and support the complexity of uncertainty management. In KBDGS, we provide knowledge-based design guidance support based on 3 aspects: knowledge classification, modeling, and capture and reuse. Now, in order to implement the KBDGS, we use 6 steps, as you can see here on the left. In step 1, we identify system concept, where we determine the design requirements for the specific domain by providing hard information such as documentation resources and soft information such as empirical knowledge. In step 2, we clarify design attributes and models of the system concept. The system concept that we identify in the first step is quantified and represented in step 2 by identifying the system goals, variables, parameter constraints, design scenarios, and so on. In step 3, we conduct the problem-solving model chain. The base entities in the PEIX diagram are used, combining the solution strategies. In step 4, we formulate and refine decision workflows based on the system concepts and model chains. We, or designers, can establish hierarchical decision workflows. In step 5, we explore the design space, including formulating and solving decision models, generating and updating design scenarios, post-solution analysis, and design space adjustments. In step 6, we improve the solution, which refers to further refining design attributes or extending the current concepts. The KBDGS prototype is implemented as a cloud service architecture with web browser-based GUI over the internet, as you can see here on the right side. To verify the efficiency of the proposed architecture, we used 2 industrial problems. The first one is hot rod rolling system design, where we focused on managing complexity, and the second one is the network manufacturing systems design, where we focused on managing uncertainty. Hot rod rolling system design is presented actually with many challenges for co-design of materials, products, and manufacturing processes in digital era. And KBDGS provides decision support in managing system complexity, process complexity, design complexity, and even organizational complexity in terms of different decision-making roles associated with materials, manufacturing processes, and mechanical engineering. More about that you can read in our paper. A second example, network manufacturing systems. There are complex processes consisting of 1 or more operations to assemble or manufacture products. Very important here is that the error can be introduced at any stage of the process and propagate through a remainder of the process, affecting the final product quality. Now, in terms of uncertainty, the frequent challenges include managing uncertainty in the simulation process parameters such as sensor noise and disturbances, managing uncertainty in the model parameters such as deviations in the position of tools and sensors, managing model structure uncertainty such as simplifications and assumptions that designers make due to the lack of domain knowledge or lack of data. And last one, managing uncertainty due to propagating uncertainty in the chain of models that we have here. The architecture KBDGS for cloud-based decision support highlights the integrated management of complexity, uncertainty, and knowledge in designing decision workflows, leveraging the PEIX diagram, as well as systematic design guidance to find satisfying solutions with the iterative process of the CDK closed loop, named FREY. There are some limitations of this architecture. It needs further improvement to ensure the universality of complex engineering systems design problems, especially in the dynamic management of decision networks. In summary, KBDGS provides design guidance to facilitate knowledge discovery, capture, and reuse in the context of decision-centric digital design, thus improving the efficiency and effectiveness of decision-making in complex engineering systems design, as well as the evolution of decision support in the field of design engineering in the age of the Industry 4.0 innovation paradigm. Where is the application areas? Well, obviously, one are the manufacturing and supply chain, but also it can be applied in healthcare, education, transportation, communications, information systems as well, as you can see here. More about this you can read in our paper. You can scan the QR code. It will take you to our paper directly. And for any further questions, we are here to answer you. Thank you.
Okay, that concludes our presentations. I will stop sharing.
Sesh, the mic is yours.
Okay. First of all, thanks very much to all four presenters. I know it has been a real challenge trying to get everything together and do the video and present it in less than 10 minutes. So thanks very much for a really wonderful presentation. Okay. So moving on to the discussion phase, I think we are pretty much in agreement that the current manufacturing systems are pretty much focused on mass production of products and with the goal of achieving low cost and consistent high quality. The challenge, however, is with the merging of the digital technology and the internet technologies with the conventional industries. It has given rise to this new paradigm of Industry 4.0. And one of the challenges is how do you ensure mass customization of products at costs that are associated with mass production. Okay, so the advent of all these technologies have resulted in enormous integration, both horizontal integration across different enterprises and the vertical integration within enterprises as well. The challenge has been most of these integrations have been ad hoc or targeted for specific industries, and there is no clear-cut framework or design methodologies behind this enterprise level integrations. Okay, so the design engineering for Industry 4.0 has to represent this human cyber-physical view of systems realization ecosystem that is necessary to accommodate the drivers of Industry 4.0. Okay, so one of the motivating factors for us when we put together this webinar has been to seed the dialogue within the design community to crystallize this notion of design engineering 4.0 and to identify the challenges to be addressed in the design and implementation of these systems. And hopefully the discussion here and in the following months will also help establish new frontiers of research in design engineering and also open new avenues for collaboration. So with this in mind, I will go ahead and field some questions for the presenters. The first question was from Dr. Wei Chen to address to Group 1, Dr. Panchal, Jitesh Panchal. So the question reads as, you have brought up many interesting research topics associated with Industry 4.0. Some of them are associated with information technologies. So what do you think are the key/unique research questions for design researchers that are beyond what we have been working on in the past many years under the guise of design science and broadly design research?
Okay. So I will start out. Thank you so much, Wei, for the question. I'll start out with the few examples of such questions, and there are more in the paper, and our co-authors can also add to what I say. I think the first topic is definitely cybersecurity. Our design community has focused a lot on functionality, but cybersecurity is something that has primarily been part of computer science and the electrical engineering community. And there are new challenges that the design community can look at, how to design products that are secure by nature, that already prevent privacy of individuals. So that's one area. The second area, I think, emerges from this integration that Jelena also talked about in her presentation, this tighter integration of customer, designer, manufacturer, and supplier. So in the design community, we have done a lot of work in design for manufacturing, where we tightly integrate manufacturing knowledge into the design. But I think now with the advent of availability of data all the way to the supply chains, can we predict trends that are going to happen in 6 months because of COVID or whatever, shortage of supply? Can we incorporate that knowledge upfront and make our products customizable so that they can be directly adapted as we see changes happening in the supply chain? So that's the second example. And the third area is as a result of new business models, new product ownership models, and how designs should be adapted to account for those changes. So I'll just stop at that and see if there are any other comments from our co-authors.
Would any of the other authors like to jump in and add your thoughts?
Yes, can I share my 2 cents?
Sure.
Yeah. As in, thanks to Wei Chen, it's a very, very good question. In fact, that was one of the motivation when our team start to think about organized special issue, and also the finally end up with a review paper and a position paper at the time. Quite true, actually, very inspiring. In fact, our design community have been observing historically so many changes and so many new phenomena, emerging issues. For example, 2 decades ago, from product family design, decision-based design. Now, what our design community opportunity out there? So, in fact, actually, our ideas think about here in response to Wei's questions here. We are thinking, in fact, one of very critical problem context. Our design somehow given so many technologies, not only decision sciences or the technology in old days, now with new IT technologies, but ultimately our engineering school research for design, we really need the industry context. That's the reason we actually consider examining Industry 4.0. That's our market, that's our working subject. By the end of review paper, which is the last sections, we did talking about the verification and validation. We are thinking our design, we want to looking for new opportunities and really profound research, close listen to the industries and examine, formulate the research problem, which is have very good validity. That'd be very, very high caliber research about the critical issues. And second observations, we are thinking, given the nowadays probably every single field taking place interdisciplinary. Conventionally, our design community mostly ME background. Then later on, pick up from IT, all those intelligent decision makings. Nowadays, in response to the other attendants get good question, what essentially 4.0 the message to us? and what different from the previously. Now the new dimension, human become an important decision dimensions in our design community. Certainly our field become more and more sophisticated, and in turn our design discipline probably in terms of enabling technology, in terms of overall the body of knowledge need to be highly disciplinary. So that's our 2 cents we are thinking to share with you. Thank you.
Thanks very much, Roger. So my take on this is the most important change that has come across in the design field is that in the past, the time frame from the design to the product, the entire product life cycle was several years, almost decades in some cases. So we had plenty of opportunity to do the design, validate the design, and if you need to revise the design, the time frames were much larger. Nowadays, most products have a shelf life of 2 years, and then we have new variants of the product coming up. So the entire design cycle is compressed. So we need to figure out more agile and more responsive ways of doing design, and how do we leverage technologies. The thing is, if I know what IT technologies are going to be prominent 2-3 years from now, I can factor that into my design. But the problem is the technologies are evolving so rapidly that it's very hard to get into any insight into what things would look like 3, 4, 5 years down the road. But I have to design systems today so that 3, 4 years down the road, the systems that are designed meet the requirements. And that's a really challenging way to look at things and way to do design, which is completely different from the way we did things in the past. So I think the speed at which the changes are coming are so fast, and how do we make sure we are agile, and how do we make sure that we are responsive? That requires a whole new way of design thinking, in my view. And if anybody wishes to add to that, that's good, or I can go to the...
Yeah. I raised my hands just to kind of say that I really like the answer that the authors have been sharing with us. I think it offers more specifics about some opportunity for the design researcher. So as you were saying that, actually, it really creates a very nice application for us to test many of the methods we have been developing for complex system design, for systems engineering. My own observation is really to bring up or emphasize the needs that design engineers, not just designing the product, say for stress, like a life of the product itself, but also the whole life cycle of a product. So that includes manufacturing, includes operation, maintenance, supply chain, right? And I think to some extent, it's really also brings up the need or the importance of system engineering. So I will just say that I really appreciated the insights that you're sharing here. Thank you.
So the next question goes to Doug. In the context of your paper, can you elaborate on why a new design paradigm, that is design engineering 4.0, is required, and why these requirements cannot be addressed through traditional design techniques? And specifically, if you can comment on the drivers of Industry 4.0 and how they influence this new paradigm of design engineering 4.0. Mr. Doug Schaefer. Jitesh, do you want to take that?
So some of the key drivers that we have sort of discussed in the paper include connectivity, visualization, and interoperability. And I think that has implications on one, how the artifacts are designed, two, how the design process happens, and three, what is the role of the human in the overall process. Similarly, there are other issues such as availability of information, big data, information transparency, decentralization, and service orientation. So these are some of the key drivers for Industry 4.0, which again have implications on design.
Thank you. Alicia Kim asked this of both paper one as well as the other authors can jump in too. The question is that the time between the different industrial revolutions, whether it's 1, 2, 3, or 4, that time seems to be shrinking and the changes seem to be coming faster and faster. So this might mean that the fifth industrial revolution may be here before we even have enough time to conduct sufficient research or to understand the full implications of Industry 4.0 revolution. So any thoughts on that?
So Farooq has.
I think Farooq had some.
So here is my observation. We have two options. One is to do things incrementally. We are doing this. This is what's in the literature. Let's add a small little bit to it. What Industry 4.0 has done is given us a paradigm shift. It's a total paradigm shift, and it's a paradigm shift that has been brought about by information technology. So if you look at design engineering, we have to think in terms of a paradigm shift similar to the tectonic paradigm shift that has happened in Industry 4.0. So if we continue to think in terms of the old questions based on where we are not going to be able to do it. So what I'm thinking about here is that we need to put together a paradigm shift community, people who want to be part of this paradigm shift. What that means is that we have to speculate about the future. We have to see what technology is coming up. We have to think in terms of mega trends. What are the trends that are going to take place? How are we going to design in 20 years from now? And then in the context of that, frame certain principles and then ask ourselves what research needs to be done. Next question. What is research in the paradigm shift that we are talking about? What is the meaning of research? Is it problem solving? Is it the creation of new knowledge? Is it transforming something? What is it? How do we define that? The third thing that has to happen is how do we educate people? Are our current modes of education sufficient? At the undergraduate level, our focus is on problem solving. 20 years from now, these are not the problems that the students are going to be solving. What is a paradigm shift in education that is going to be required? One possibility is to say, hey, we want to empower students to learn how to learn. We want to empower students to learn how to speculate. We want to empower students on how to ask questions, listen, and identify gaps. We want to empower students to make decisions using incomplete information. We want to empower students to use critical thinking within themselves in terms of saying, what is it that I need to learn to bring about the paradigm shift? And two, if somebody gives them a paper to say, hey, this is what are the holes in it? Why will it work or why should it work? So I think we have to take a systems perspective to make this happen. And the solution is not just in engineering or mechanical engineering. It requires people from different disciplines to get together and say, this is the future and this is where we need to go.
Thanks, Farooq. Anyone wanting to add to that? Faiz, Wei? You guys have the big picture view, so. Okay, so moving on to the next one. This focuses more on testing several designs at the same time and so on. So one of the key requirements of design engineering 4.0 that's motivated by Industry 4.0 is the ability to generate and validate several designs at design time. Further, these designs and their corresponding models should be modifiable based on the feedback from the manufacturing process. And this modification has to be pretty much in real time. So in recent years, manufacturing has become a critical component of cyber, physical, human, social infrastructure. And in this, the first two elements, which is the cyber and the physical parts, they are engineered or known quantities, while the human and the social structures are notoriously unpredictable. So the question for Dr. Heydari is, in the context of your paper, can you elaborate possible ways in which design engineering 4.0 can address dynamic management of engineered systems? So what are the salient features of these frameworks, architectures that you need for learning and adaptation in real time? Because this thing has to happen in order to test different designs and to validate them and to modify them.
So I think this is something that my colleague, Professor Mogatem, is better suited to answer.
Sure. Yes.
Hi. So could you please repeat the question?
Yeah, so basically there are four different elements to this cyber physical human social infrastructure. You got the cyber and the physical ones, which are fairly well understood because they're engineered or they are physical systems that can be studied. The human and the social side are notoriously unpredictable. Now, if you're trying to design systems to address all four requirements, and two of these requirements are totally unknown or changing, right? What type of architectures do you need, and what are the challenges in adaptation and learning in this environment?
Right, that's a great question, and that's I believe one of the main problems that this paper tried to, at least at a basic level, address, and that's that in Industry 4.0, in modern factories right now, I mean, collaborative robots is actually one of the driving technologies in this case of the human and social, like the human element of the manufacturing process. Collaborative robots right now, to my knowledge, in modern factories even, are mostly being used. They're not being used to their full potential. So they're being used mostly as tools that are there to do repetitive tasks. There are simple interfaces for programming. There are safety features for them to work closely with humans. But the fourth level of human-robot collaboration, which is like the cooperation in a shared workspace and working on the same task, has not been realized. And part of the reason is that involving a human in this process inherently adds more unpredictability, more sort of variability, makes the process more unpredictable. And there is a need for more flexible automation, more adaptable automation, as we have sort of proposed in this paper. So one of the potential architectural frameworks to address this gap would be the idea of modularity. So reinforcement learning, in the case of our work, addresses the idea of adaptability. And adaptability, what we mean in this case is that involving a human in a workspace in the process that is mostly automated using a collaborative robot introduces some variabilities in terms of the variation between the base and tool coordinate system, tool center point of the robot, adding more like sort of like physical variability to the task that could be a pick and place, could be an assembly, etc. But the problem is reinforcement learning by itself cannot necessarily solve this problem because it takes a long time to do reinforcement learning, to train a reinforcement learning algorithm on this idea of task personalization, this limitation of task personalization in reinforcement learning basically limits large-scale adoption of this technology to address the adaptive need for human-robot collaboration. And that brings us to the modularization aspect, that there are probably hundreds of different tasks. I mean, robotic operations in manufacturing are mostly either workpiece handling or tool handling from like machine tending, assembly to machining processes, welding, etc. And there are probably hundreds of different variations of these applications. But if you break them down into modules that are shared across all of these tasks, we should be able to address this issue of the limitation of current learning algorithms, reinforcement learning algorithms, to transfer from a source task to a target task, from, for example, an assembly task to a machine tending task, and sort of like reuse some of those learned policies, trained neural networks in other tasks that share some similarity in some modules of their overall task structure. I hope I answered your question, at least like partially, and I'll let my colleague Babak and our PhD student Qiliang to chime in if they have any additional points to make.
So, do you see? I certainly understand and appreciate that we need to think in modules and try to find modules that can be shared across different applications or different systems so that we can leverage the knowledge across several different applications. The question is there a limit to where you can do these things where the cost might start outweighing the benefits that you're going to get? Because this is a very laborious process.
Sure. So let me actually add to what Mohsen said about this. So there are two things I think that will limit the practical benefit of and scaling up this approach. The first thing is that so currently we are defining the modules before starting the process, right? So and so we can only do this for the environments that are up to a certain level of uncertainty. If the uncertainty grows, then it's very hard to predict the modules and the boundary of modules up front. What we need to do is to allow the system to redefine the boundaries of the modules constantly. And that is something that we don't know how to do yet. So we have a theory, some past theoretical work that shows that dynamic modularity and evolvable modularity is actually very beneficial. And the example is just human brain, right? So human brain deals with the ultimate level of uncertainty, and the way that it deals with modularity is going from the fixed level of modularity that we see in the other organs to dynamic and evolvable modularity on a constant base, like reclustering these neural nets. So that is something that we need to add to this level, to this model. That's number one. Number two is when we want to bring in human interaction, especially in human interaction when we have kind of like hybrid modes of interaction. Hybrid mode is when we have both a combination of collaboration and competition. In those cases, if we want to train a model, we need to have a realistic digital model, computational model of human behavior. So, and we know that any realistic computational model for human behavior is challenging. So there we need to borrow from recent advances in computational cognitive science to bring in these models to be able to simulate, hundreds of thousands or millions of rounds of these reinforcement learning by adding this by incorporating the computational models of human interaction. So these are the two challenges: dynamic modularity, computational models of human cognition.
And if I may, I would like to add just one more point to that in terms of like the trade-off, right now, if you really just want to approach this problem with existing reinforcement learning technologies, basically, as I mentioned, there are hundreds of different variations, but at the same time of tasks, robotic tasks in manufacturing, but at the same time, there are only around 10 to 15 main types of applications in manufacturing, being machine tending, being assembly, welding, painting, etc. So the idea here is that this is, as I mentioned, this is a very preliminary work in this area, but if this idea is successful, if we are able to successfully modularize, and in the case of manufacturing, we're talking about Industry 4.0, we don't want to overcomplicate the problem, or we don't want to introduce problems that do not necessarily exist in practice. So the problems here are that there are 10, 15 major applications of robots in manufacturing. And if we can successfully modularize these tasks and pre-train those policies on those modules, and then the question becomes, how do we then compose them? Then we could have, instead of a robot trained using reinforcement learning on this particular task, we'll have a robot that is a machine tending robot, but not an existing machine tending robot that is programmed using a pendant, a machine tending robot that knows machine tending. So it could be many different variations of machine tending, but the robot can quickly adapt to them. So in terms of cost saving, right now, to my knowledge, at least in industry, there's very minimal applications of AI. There are other types of AI, computer vision, for example, or even some natural language Dialog, but reinforcement learning for robotic control, to my knowledge, it's not adopted. It's at least like it's not adopted to its full potential in industry. But this idea could potentially lead us towards that.
So, sounds good. Interesting. And again, one of the challenges that I see is this area has become so multidisciplinary that it's very hard to draw the box around and say these aspects are purely computer science or neural networks or AI or whatever else it is, and these are purely design. It becomes very hard to find the interface between different disciplines, especially when it comes to design and manufacturing. Interesting topic. I think we'll have a lot more in the breakout area after we are done with this discussion panel. So moving on to the next question, we get to applications. For Dr. Song, there's a question for you. Can you give examples of the decision support system that you can provide in real time, and how the role of physics-based simulations and what role the physics-based simulations can play together with the physical data? And again, what type of methods do you intend to use for decision making?
Yeah. Okay. Thank you. Thank you, Professor Chen. I think that's a very good question. The current work or the current system, I think we can provide some useful decision or information, like the uses the life of the structures or the strength distribution of the main or critical components. So we can provide the information to the customer, and the customer will decide how long this system will last. And in the next loop, when we try to design a new product, we can enhance the structure or in that area, and that decision will be very useful. And for the second question about the physics model and the date, I think actually the ideal condition actually is we don't need install any sensors to a real physical system, because that will cost a lot of money and cost a lot of time. So in the real applications, the sensors will not work very well for a long time. So we have to rely on the physics models, but the physics model is not that accurate. Actually, we have some assumptions or simplifications. So the best idea, I think, is to combine them together and maybe think like this. We can calculate based on the offline simulations with the physics models, then give a strength, for example, the strength distribution and the trend of the strength. Then we can deploy this system online, but this one is not that accurate. So we can use a few of sensor information to calibrate them. So that's the basic idea of the multi-fidelity surrogate model, or the very popular transfer learning method. So yeah.
So what are the challenges? So if you're trying to create these models, whether digital twins of different modules or different physical processes, if you have to create several different modules with several different resolutions and stuff like that, what exactly is the effort that's involved? And you are trying to do it for multiple fidelities, and you are trying to model multiple physical processes together, where the interface between the processes themselves is fluid. So easy to, again, it's just way out there. If you have a specific component with specific functionalities, it's fairly easy to design a digital twin for it. But if you're trying to address all the unknowns and you're trying to come up with different variants of the same part with different fidelities, different functionalities, what is the effort involved? And is there a point of diminishing returns?
Yeah. That's a very good question and difficult question actually. To be honest, we didn't consider all these effects because it takes a lot of effort or time to handle. So we in our demos you can see that we are doing some structure. Actually, it's a structure digital twin because we find that the structure is easy to deal with. And if you want to do more physics like the fluid or like the thermal, the temperatures, that will cost so much computational resources because the temperature or the flow is actually it's not loading at one point. It's a surface loading or surface problem or volume problem. So I think we can deal with maybe in the coming future that using some parallel computing, or we'll move them or copy all the calculation to the in a cloud system. So we calculate them in the cloud system and then send the result to edge system. So we can do edge or cloud collaboration.
Moving on to the next topic here. This goes to Jelena, and then maybe Jitesh can jump in after that. The question is, in the context of your paper, can you elaborate how dynamic management of engineered systems can be accomplished? That's a critical thing. And what are the new frontiers in research that you think need to be addressed if we need to develop this ability to manage the dynamic nature of the systems?
Can you hear me?
Yeah, we can see you, but we can hear you.
Yeah, I am fortunately in the car. I apologize for that. It's just obligations. Yes, so in the context of our paper, so what we discovered that the traditional domain knowledge and domain dependent calculation analysis should be actually integrated dynamically. So we noticed that there is a need for that in order to support decision making in this new age that we call Industry 4.0. And you can see in our paper the example that we used, especially the hot rod rolling system design. We saw that decision makers for the steel manufacturing process should be aware of design set points for each unit operation in the plant scale production of steel products in order to realize this dynamic management based on the cyber physics. So this requires exploring the design set points and anticipating the results produced by systematic design space exploration. So what we did with KVDGS, we implemented integrated management via the CDK closed loop framework and systematic design guidance or FRAME method to increase the efficiency of information interaction and design iterations in order to enhance the insights of decision makers. So that is what we did specifically in this paper regarding the dynamic management in knowledge exchange.
Thank you. So to conclude, the final question that I have is that, again, it goes back to the time scale that's involved with all these changes that are coming across, right? So the technologies that are driving the changes in design engineering, these things are coming much faster than the timescales that are typically seen in design and manufacturing. And most industries today are at a very low technology readiness level to leverage the advances in design engineering 4.0. So, and I'll leave this open to any of the authors who want to jump in. I'll try to keep this to about 5 minutes, and then we'll wrap up and go to the discussion forum outside of here. So the question is, what are the new frontiers in research that must be explored to facilitate the implementation of design engineering 4.0 principles and designs, especially given the fact that most of the manufacturing industries are at a very low technology readiness level to implement these designs. Who wants to go? Jitesh, Dirk, anyone? Farooq?
I think this is a good question for the leadership in ASME. So, for example, Carolyn Sipasad, or who's coming in as the next editor of the JMD, or Wei Chen, or George Hazelrig. So I would open this up to invite Carolyn, George Hazelrig, and Wei Chen to answer that question.
I think that's a good idea. Yes.
So Carolyn, as the incoming editor-in-chief of JMD. Wei, as the outgoing chair, editor-in-chief of JMD.
Would you please just to kind of repeat the question one more time? I guess, you know.
Sure. So the thing is, the changes are coming at a very rapid pace. Even if design engineering, as you see it, can adapt to these changes, the industry itself is at a very low technology readiness level. So what are the challenges that we need to be able to address in order to transition these design engineering principles and designs into practice?
Yeah, so, you know, I would say that many of the fundamental issues that industry faces in design engineering are something that we have been aware of, or we have been working on very hardly, you know, in the past. You know, I think that this design as a research community by itself starts from 1980s when NSF first established this program, right? So I believe that we have been working hard on many of the fundamental issues. On the other hand, the society change continuously, new technology coming up continuously. So as design researcher, we have to always be aware of what are the applications that can make important societal impact. And for doing that, we do have to work closely with industry to bring our methods to the reality and integrate with the current technology. So on the other hand, you know, if we're talking about in design, we have this we call the normative approach versus prescriptive versus descriptive methods, right? As design research, we are always interested in normative approach, which means we have to think ahead of industry, right? We're looking at the ideal, rigorous way of doing things, and we're not working on method that just try to kind of observe how the work are done currently in industry. So we have to think ahead. But on the other hand, I think this requires to do this successfully requires it's a two-way thing, right? We have to work with the industry very closely in order to ensure our methods are applicable. George, you have something to add to this subject? You have been here for a long time.
I'd come back to Farooq's comment about we're teaching engineers to be problem solvers. And I think that that's a problem. We kind of agree, I think, that design is largely a process of decision-making, but we don't teach decision-making. And we graduate engineers with virtually no understanding of preferences. You can't make decisions without preferences. And so they go off and they have no clue how to use the notion of a preference in decision-making. Also, decision theory is all about dealing with uncertainty. And I don't think we're doing a good job of teaching probability theory or the treatment of uncertainty. So, you know, we leave these gaps in education of people, and then we send them out and expect them to keep up with the technology. I don't think it's going to happen. We need to revise our educational process.
Thank you, George.
Yeah, I want to add one more thing. I feel like it's not only just working with industry. I feel in order to succeed in design research, just today's topic, you can see it covers manufacturing, it covered supply chain, many other disciplines. As design researcher, we have to be open-minded to work with researchers from many other disciplines in order to address the problem.
And the other thing that important thing is it's become global, right? It's just not working with people from different walks of life or different expertise, but also from different nationalities, different cultures, different geographic domains, and this thing makes it really, really hard.
You know, one of the things about decision making is whereas problem solving is disciplinary, and we teach it in a disciplinary way, all decision making is what I refer to as omnidisciplinary, which is to say, every decision you make must take into account every conceivable discipline, which is actually not possible to do. But at any rate, that's what it's about.
Yeah.
Thank you. I think it's time. We have 4 minutes overtime for this session. So Janet, you're closing. Unmute yourself.
I think the 12:30 session for GatherTown starts. But my closing note, I just want to say a big thanks to Amy, to Wei, to all the organizers, to the presenters, to even all of the guests. I am not an engineer. I got my degrees in literature, so everything goes over my head here, but I do learn something new every time. So and just having communities come together online is really nice to see. So big thanks on behalf of ASME, and have a great day, everyone.
Did you ask for Janet to say a few words also? Yeah. Yeah, Janet.
Yeah.
Please.
So on behalf of the 7 co-editors of our special issue on design engineering in the industry of 4.0, I want to thank everyone involved also. Wei Chen and Amy Susky for the advice and assistance with this special issue of Journal of Mechanical Design, Fayez, Amy, and Jenna Sayer for assistance with the webinar, which went very well. I also want to thank the 56 authors of the 14 papers in the special issue. We have put this special issue and webinar together to provide a repository of information for the design community about design engineering 4.0. We thank the reviewers who lent their expertise and helped us select the 14 articles from the 33 articles which we received. We have put more than 950 articles have been referenced, and many, many avenues for research are proposed. It is our hope that in this special issue and the webinar, we will provide a starting place for our journey together in defining and exploring design engineering 4.0. Now, to close the session and continue the dialogue, communication on the GatherTown app, I turn it over to Fayez Ahmad. Fayez?
Yes. Thanks, Janet, for the handover. So I've sent the link in the Zoom chat. I'll just type it again for everyone to see. What we'll do is we will have a social gathering where people can move around and talk to each other in a more informal setting. To demonstrate how GatherTown works, I will share my screen right now and click on the link. And once you see a quick tutorial, you can try it for yourself. So I'll close my video and start sharing my screen in a minute.
Yeah, while Faiz is doing that, I just want to remind everyone that all the talks will be available at the JMD companion website, the asmegmd.org later on in a couple more days.
Right, so hopefully people can see my screen right now. Once I click on the link, I have this option of clicking on join event. I click on that, and you will see immediately that the webinar comes on. I will, in this particular case, I'll see what camera and what mic is there, and I will just switch on my video in this and do join the gathering. Now, once I click on it, I'll reach a room. And as you can see, I can see Farouk here on this side. So I want to talk to him. I'll use the arrow keys of my keyboard. So I'm clicking on the arrow keys and I can move around. And if I go close to Farouk, you will see that I'll connect with him on a video call. So you can immediately see right now that I can see his video call, and right now his camera is switched off, so we can, once it's switched on, we can talk. So that's pretty much it. And the idea is that you can move around just like in a conference and form small circles. Specifically, the speakers can spread around, and if you have any questions, you can talk to them, or so on. One thing to note is you see these blue rooms, and these blue rooms are the ones where if you are inside this room, it's a private chat room. Outside these, if you are close to anybody, you can talk. It's kind of like a conference. You have a more private area versus you have a general area. And there are two rooms in this. So right now I'm getting close to Jelena, and I can connect with her, or I can go to this other room, which is where everyone enters. So that's it. I will stop sharing my screen now, and please switch off your video and audio on Zoom before connecting to that, and check that your video and audio is working. I believe, so I'll keep my Zoom on, and if Amy will most likely, if you can also be here in case anyone has questions, you can come back to Zoom and enter it on chat. And for the next 5 or 10 minutes, we'll try to debug any problems with gather.town. And then we can be there to meet you. Thanks, everyone.